In this discussion video, we'll do an optimization problem involving a rectangle that's inscribed in a circle. So the problem asks us to find the maximum area of a rectangle inscribed in a circle of radius 10. So I want to first give you 6 minutes to try this problem. Pause the video in 4, 3, 2, 1. Pause it and try it for 6 minutes. Alrighty, so hopefully you did that. Hopefully you paused it and tried it for 6 minutes. If not, I really encourage you to do that. It's super important, especially on the more challenging questions or topics like optimization, to constantly assess how well you're understanding the concept. So if you haven't tried it, definitely try it. Don't be discouraged if you get stuck. That is okay. Really take those 6 minutes to try the question. Alrighty, so hopefully you did that. Let's talk about it now. So first, we want to identify the thing that we are trying to optimize, the thing that we want to maximize or minimize. In this question, that's the area, and we want to maximize. We want to maximize the area. Okay, and now let's draw a picture. So this problem says we have this circle. And then in the circle, we have this rectangle that's inscribed. Okay, so I'm going to draw this rectangle. Okay, so maybe something like this. So I want to avoid making assumptions like, is the rectangle a square? I don't want to just make assumptions like that, because maybe it's not. Maybe the maximum area rectangle is not a square. Okay, and now, well, let's put some variables in here. So I know, maybe I'll call this x, this length, and then I'll call this vertical length y. And then I know the radius of the circle. The radius is 10. So the radius is 10. Okay, and from here, let's form the objective equation. So the objective is an equation for the quantity that we want to maximize or minimize. In this problem, that's the area. And in terms of my variables, the area of the rectangle is x times y. So what I don't like about this is in terms of two variables on the right-hand side. I want it in terms of one variable so that I can use our methods for maximizing and minimizing involving taking a derivative, getting some critical numbers. So the way we do that is I need some other equation, which I call the constraint, that we get using information in the problem. So I'm going to give a hint, an important hint. I want to somehow use the geometry of this picture to get another equation. And it's going to be helpful to draw the radius in a better way than I did. So I drew it sort of slanted like this to kind of some random point. So let me draw the center one more time. So my hint is to think about, is there a better way I could draw the radius so I can use the geometry in this picture? So I want you to pause the video for 1 minute to think about that. That is the heart of this problem. Definitely utilize this 1 minute to think about that if you haven't already. 4, 3, 2, 1. Pause the video for a minute to think about what's a better way to draw that radius. Alrighty, let's talk about it together now. So the nicest way to draw it is to draw it to this corner, because I know that length is 10. And if I keep extending it all the way this way, I form this diameter, and that's 10. And this is a right angle, so we get this nice right triangle, where this is 20, this is the diameter. This is x, this is y, and now, because it's a right triangle, we can do Pythagorean theorem, which gives us x squared plus y squared equals 20 squared. We got this other equation. Okay, so drawing that diagonal line was really essential here. Okay, so now I need to isolate one of the variables in the constraint. So if I isolate y squared, I get it's 400 minus x squared. And if I square root this, we get y equals the square root of 400 minus x squared. We don't need a plus or minus. No plus or minus since y is a length. So now we're ready to take that constraint and plug it into our objective. So this will give us that our objective, A, is x times y, and y is the square root of 400 minus x squared. So from here, we need to do things like find critical numbers and test them to see if they give us a max or min. If I were to take the derivative of this now, we could do it, and we get an answer. It's just going to be tedious, because I have to do some product rule, there's the square root of some stuff. But we've seen a way to get a shortcut around situations where we have a square root of some stuff. And the idea is, instead of trying to maximize a, let's find first the maximum of a squared. So e.g., for example, if the maximum of a squared is 81, if that's the biggest, whoops, let's write that squared better. If the maximum of a squared is 81, then we can quickly get the max of a. If the biggest a squared ever got was 81, the biggest a ever would get is 9. And this is assuming, of course, that if the quantity a is non-negative. And in our problem, that's going to be the case because a represents the area. It represents the area of this rectangle, and that's definitely a non-negative quantity. Okay, so what I'm going to do is I'm going to square both sides of this equation. That'll give me a squared equals x times root 400 minus x squared, that quantity being squared. So when I square this, because these are multiplied, I square each of them. I get x squared times the root squared. So the root goes away, and I get 400 minus x squared. Okay, so a squared equals, let's distribute x squared to get 400x squared minus x to the fourth. And now it's fully simplified. We are ready to take the derivative. So I'm going to take the derivative with respect to the variable x. Okay, when we do that, we'll get the derivative of a squared, I'm just going to write a squared prime, equals 800x minus 4x cubed. So I'm now just thinking of a squared as its own function. I'm thinking of it like f, like maybe this is f prime, or thinking of it as like a function like g, like maybe this is g prime. Okay, so we've gotten the derivative of this function. We need to find critical numbers, so let's factor it. So I can take out a 4x and be left with 200 minus x squared. And from here, I'll be able to figure out when is this equal to 0 and when is it undefined. So our derivative equals 0 when, oops, let's space out that when from the front, it's when x equals 0. And then from the x squared minus 200, we would get x's square root of 200 as well as negative 200. But x can't be negative. X can't be negative, so when I square root to get that plus or minus, I don't put the plus or minus because x can't be negative. Okay, and our derivative is never undefined. We don't have anything like a denominator here that could possibly be 0. Okay, so we are going to need to test our critical numbers. Test our critical numbers. And in this case, we actually have two critical numbers. There's one when x is 0, there's one when x is square root of 200. So one thing that's going to help me decide which method to use is, let's first think about, well, what's my interval for my variable? And our variable that we got it in terms of was x. So if we go back to the picture, and if I think about x is one of the lengths of this rectangle. Well, the smallest that could be is 0. If it was 0, I'd get a degenerate rectangle. And the biggest it could be is if x became like the whole diameter, which is 20. And that would also give me a degenerate rectangle. Okay, so our interval for x is going to be 0 to 20. And I can make it a closed interval because that just gives me degenerate rectangles, which are fine. Okay, so I'm going to use the closed interval method, which we had called our first method for testing. So we're going to use the closed interval method. Plus, and that involves the extreme value theorem. So that the idea there was you take your endpoints as well as your critical numbers, you plug them into the original function to see what the biggest output is and what the smallest output is. So our endpoints are 0 and 20. Our critical number is square root of 200. And square root of 200 is in between 0 and 20 because 20 is square root of 400. So square root of 200 is between those two. That's good. Okay, now let's plug them into our function. So I'm going to plug them into the a squared function. So let's recall that a squared was x squared times 400 minus x squared in that factored form. So if I plug in 0, we'll get a squared equals 0 squared times some stuff. It doesn't really matter what that stuff is. This is going to be 0. If I plug in 20, we'll get a squared equals 20 squared times 400 minus 20 squared. But 400 minus 20 squared, that is 0. So this is also going to be 0. But when I plug in square root of 200, and by the way, I would say, so those also I think make sense. When x is 0 and when x is 20, we said earlier that those are degenerate rectangles. So it makes sense that their area squareds are 0. Okay, if I plug in square root of 200, we'll get root 200 squared times 400 minus root 200 squared. Okay, and if we work this out, the first root 200 being squared is 200. And then this whole thing in parentheses ends up being 200 also. So we'll get 200 times 200, which is 200 squared. So what we found is that the max, so by the way, the biggest of these is 200. This is the max. And because we're doing the closed interval method, this also gives us the mins. The mins occur here as well as here. The minimum area squared is 0. Okay, so the max value of a squared is 200 squared. We needed the maximum value of a, so we can just square root this. That's the biggest value of a squared. The max value of a would just be 200, or the square root of that. And that is what the question wanted. It wanted to know the maximum area of such a rectangle. And we got it.